in the global scale. Now, what are those sectors that are energy intensive, and how this can be replaced with using the hydrogen is shown in this graph on your right hand side. So you can see with the time, you will see that the change in the energy mix, especially the percentage contribution of the hydrogen in the existing tech industries like transport, power generation, ammonia production, or in the grid injection, or in the buildings and in the refineries. So let's see for the industry. So you can see that the industry requires fuel, whether it's fossil fuel or renewable energy. But the estimate shows that the industry will require, currently it's from around 51 million tons of hydrogen. So they will need around 140 million tons by 2050. So this is kind of a substantial growth in the industry, and mainly because of the demand in shifting to the decarbonization of the industries. The other sector would be the transport, right? Even though transport has a very small amount of in the hydrogen, but in the future it will be a major market for hydrogen, and that's around 100 million tons in 2050. Now, refineries will be the interesting, because as you can see that mostly oil refineries are now using fossil fuel oil, but in the future they will not be able to use oil to refine. So therefore, you will see a drastic reduction in the amount of oil that is required. So the same thing, you will see there is a decrease in the amount of hydrogen that is required to run these refineries. So that's only the major standout of hydrogen demand in the refinery sector. Now, ammonia as a fuel, yes, ammonia will be the future for producing urea as a fertilizer, and also for the transport sector, especially the shipping industry. So you will see ammonia would be the major fuel in the future for transport, especially the long distance transport by the shipping industry. So you will see a drastic increase in the ammonia production. Now, what are the pathways? Now, as I said, that currently we actually use only the fossil fuel energy to produce hydrogen, right? Around 90 million tons of hydrogen was produced in 2020, and that almost 80% came from fossil fuels. But in the future, as you can see, that there will be only mainly 3 technologies that will be used. The electrolysis, which is basically using solar energy and splitting the water molecule into hydrogen and oxygen. So because you're using solar energy, it's a renewable energy source. So you are actually consider it as a green hydrogen. Now, the other 2 pathways are considered as the thermochemical. Now, one is the gasification. So that is you are actually using the natural the biomass and gasify it to produce hydrogen through syngas. And the other one is using the natural gas, methane, and then converting that into hydrogen using steam methane reforming. So these are the 3 main technologies. They have their own advantages and disadvantages depending on how you see it. For example, the electrolysis is considered as the more clean technology, but you need a lot of water, right? So the water footprint is really enormous. And you can see that you need about 9 kgs of water to produce 1 kg of hydrogen. So this is where people are trying to understand, if you are heavily dependent on only electrolyzers or electrolysis, then where is this amount of water that can be produced? So some are thinking of using seawater and using desalination plants to produce this water, and use that water to produce hydrogen through solar electricity or through wind electricity. And then it is estimated that from 0.03% current hydrogen production through electrolysis, we may need to jump to 61% by 2050 to meet our hydrogen demands. Similarly, the gasification and steam methane reforming, they also have large footprints either in terms of the water requirements or also the carbon dioxide emissions. So for gasification, you need around 40 to 85 kgs of water to produce 1 kg of hydrogen. And for steam reforming, you need 13 to 18 kgs of water to produce 1 kg of hydrogen. So these are those kind of technology. They are available now, and they are almost in kind of what do you call full scale. Soon they will be a kind of industries that are actually developing around on these three technologies. Now, the cost of production of hydrogen, this is the main driver for fine tuning the technologies so that we actually can achieve the minimum the ideal targeted cost of production. Now, at the bottom of the screen, you can see the hydrogen production cost as per the US, the benchmark is around $1 per kg of hydrogen. And that's the goal we have set in, because currently we produce hydrogen from natural gas in the fossil fuel gas, around 0.5 to $1.7 per kg of hydrogen. So that is the fossil fuel electricity. But as the renewable energies technologies are very expensive, so you will find it very difficult. So the cost of production of renewable hydrogen is here, around $3 to $8 per kg of hydrogen. But the main cost of that, the hydrogen production, is the electricity. So if we can handle that electricity production costs by 50 or 90% reduction, so you will be able to cut down the total cost for the hydrogen production from renewables. So this is the green one, what you see. So we are at this moment here at around $8, from $3 to $8 per kg, but our target is to bring it down to around $2 per kg of hydrogen. So based on this idea of how much the target that is set is to Australia to bring the cost of hydrogen production to $2 per kg, I started to work on a new project, and the results of that project I am presenting. Now, earlier in the slide, I told there are three technologies that are used for hydrogen production. That is the electrolysis, the other one is gasification, and the third one is the steam reforming of methane. Now, I'm going to present a way of producing hydrogen using microbes. Okay, so we can also use bacteria to produce hydrogen biologically. Now, what you're seeing on this slide is called the anaerobic digestion technology. This is basically a microbial process where bacteria convert the organic matter into biogas under anaerobic conditions. Now, this biogas is mainly made up of methane and carbon dioxide. And this is the standard way of what we produce. All these four reactions that happen in this biogas process will show that there is some hydrogen production in the pathways. But what we do is we optimize the processes in such a way that we can actually produce hydrogen and methane in the same AD process. And then the produced hydrogen and methane can be used for heat and electricity production, or even cleaned up and use it as a vehicle fuel or injected into the grid. Now, how do we do it? So the same process, what you saw earlier, I am trying to block the utilization of the hydrogen, right? So in the earlier slide, you can see a lot of hydrogen is produced during the conversion of sugars, amino acids, and long-chain fatty acids to organic acids and alcohol. So that hydrogen will be consumed in the end by methanogens to produce methane. Now, what we need to do is to to separate these bacteria into not able to utilize this hydrogen. Okay, so there's methanogens which will need to use this hydrogen and carbon dioxide to produce hydrogen. We will separate them into two stages. So this is what I'm showing here. Normally, all the reactions happen in one reactor, but now we separate them into two processes. So you have the hydrogen production in the first stage, where the hydrolysis and the acidogenesis and estrogenesis of the materials, organic materials happens. And the last one is where the organic acids that are produced will be fed into this second reactor, and you produce the methane. So this is called a two-stage anaerobic digestion process. So the goal of this project is to produce hydrogen and methane through two-stage anaerobic digestion of the lignocellulosic feedstock. Now, what I did is that I have collected a lot of feedstocks from in agriculture or even from the sugar industry. So a lot of lignocellulosic, so almost 20 something odd feedstocks. You can see that they are from sweet potato, carrot, cassava, sweet sorghum, sugarcane industries waste, and also some weeds from the roadside, or even the agriculture waste like wheat straw, oat straw, and like that. So all that feedstocks we have screened. So we use this kind of studies where we add bacteria, mixed culture bacteria that is rich in producing hydrogen, or which can also produce methane. So we put them in separate assays. As you can see, these bottles. So the 24 agricultural lignocellulosic materials are incubated in these batch reactors with the bacterial culture, and then we monitor the gas production. So you can see here the hydrogen production curves for all these feedstocks, right? So with time, you'll see the gas production is evolved over a period of time. And among these 24 feedstocks, I see that wheat straw was the best. Okay, so among these 24 feedstocks, I see that wheat straw was the best feedstock because it has produced much higher amount of hydrogen per gram of material, and that is what I have kept in mind. And then we do the same thing for the methane production assays, and you can see the 24 methane production assays are here, and the gas production evolved over a period of time. And then I also take the amount of methane that is produced, and then in that also I see that wheat straw came as number one, the amount of methane that is produced. So from both hydrogen and methane production, wheat straw was the best feedstock among these 24 feedstock study. So you can see here also the hydrogen content. So in the biogas, how much hydrogen and carbon dioxide is present, or how much methane is present. So we can see that in terms of hydrogen content, the cassava has the highest hydrogen content, followed by wheat straw and barley, right? So the blue bars shows the amount of hydrogen content in the biogas. On your right-hand side is the methane content, and then you will see here all the circles shows the methane content, and in that also you'll see that cassava is the highest methane content. So what it shows that the feedstock characteristics plays an important role in the amount of methane or hydrogen production, right? So the carbohydrates or the feedstocks that have highest amount of carbohydrates will give you the highest or best methane and hydrogen yields compared to other materials which have low carbohydrates. So starch and carbohydrates are the best, followed by protein, and then the last one is the lipid content. Now the based on the organic matter, the hydrogen and methane yields are shown here. So you can see that based on the organic matter. So organic matter is the actual material that is actually converted to methane or hydrogen. That is the organic matter, right? So based on the organic matter, you will see that cassava plant, it has the highest hydrogen, followed by barley and wheat straw. But based on the fresh matter, the amount of material, the fresh matter, you will see that wheat straw came the first, as I showed you earlier. So wheat straw followed by barley, right? And then you have the sweet sorghum. So you can also see that it's the same trend for the methane also. So that's why the better the carbohydrates, or the higher the amount of carbohydrates or starch, the better the hydrogen or methane yields. So from the batch studies, you move on to the reactor studies. So what is now, we know that wheat straw was the best substrate. So we move now to the two-stage reactor study. So as you saw earlier, that we should have 2 reactors to study this process. So the same thing. So we'll have a small reactor to produce hydrogen and a larger reactor to produce the methane. So I will use the wheat straw as the feedstock, and that's my first reactor where hydrogen is produced. And this is a big reactor, which is the second reactor where the effluent from the first reactor is fed to the second reactor. So then I produce the methane in this reactor. So the conditions are here. So the small reactor, where it's called as a hydrogen reactor, is only 2 liters, and working volume is 1 liter, and I operate at 37 degrees Celsius, and the retention time is around 2 days. So these are more technical terms that are used for operating a biogas reactors. Then we monitor the gas production. What is the quality of the gas production? What's the hydrogen content? What's the pH? And we have to optimize the process. Okay, so this is basically, as this conference is about how to optimize a process using the data. So this is how we actually optimize the process. So it is not a blindly running in reactors, but we need to take the data and then control the process, bioprocesses, so that you can actually optimize the hydrogen and the methane yields. So on the left-hand side, this whole chart is for the hydrogen reactor. And on the right-hand side, this whole chart is for the methane reactor. Now you can see on the top, we are feeding. This is the amount of material that is fed, is shown in the black lines. And then you can see the amount of hydrogen production. So hydrogen production increase with increase in the amount of material that fed to the reactor. And then you can also see what's the hydrogen content in the gas that is produced. So you can see that it increases steadily with the increase in the amount of organic material that is being added to the reactor. So if we notice that we get at least 50% of the gas as hydrogen, and that's really excellent, because if you want to feed it to a natural gas grid, the maximum amount of hydrogen that you can feed is 10%. And mixing the hydrogen with the methane, which nowadays we call it as hythane. Hythane means hydrogen and methane. Okay, we combine these 2 terms together and call it as hythane. So the mix of hydrogen, 10% of hydrogen with the biomethane, will improve the calorific value of the gas when you are injecting into the natural gas grid. So that's why we are doing this research to see that whether we can get a high quality biogas that contains hydrogen and methane. So this is one of the most important characteristic of this biogas hydrogen reactor, is that it is optimized to produce hydrogen only at the pH of around 5.5. And you see a lot of organic acids are produced. Now, these organic acids, they are not consumed in the hydrogen reactor. So that's why we are connecting that to the second reactor where all the organic acids like acetic acid, propanic acid, butyric acid, they will be converted into methane in the second reactor. And then you can see that the methane production also increases with increase in the feeding rates, and it stabilizes because we are only feeding at a fixed rate of 2 grams of organic matter per liter per reactor. And it has a very good methane content. It also has more than 50% methane. So overall, it shows that the two-stage hydrogen and methane production is feasible. Now let's do what's the actual values we see. So for us, we saw that the methane content, the hydrogen content is good. We can get around 36% to 44% of hydrogen in the hydrogen reactor, and then about 50% of hydrogen in the hydrogen reactor. And the yields are also excellent. We can get about 63 milliliters of hydrogen per day of hydrogen, or around 240 to 271 milliliters per day of methane. So using that data, we try to can create a what we call a feasibility study. Wow, so that means that is that feasible? Can we use this two-stage biological process where the bacteria actually convert the organic materials from agriculture waste to produce hydrogen? Now the targets of hydrogen is, you can see that we want to produce around 220 kg per day of hydrogen, and the cost of production has to be around $2 per kg of hydrogen. So with that, I made this big kind of feasibility study, and you have my first reactor here, and it has to be around 260 cubic meters. And then I have two second stage reactors, that is two methane reactors of 3,000 cubic meters. So you can also have 6,000 cubic meters of one methane reactor, or you split that into two. So overall, we need around 17,500 tons of sugar wheat straw per annum to achieve this 220 kg per day of hydrogen. So the material will be fed to this first reactor, and then the effluent from this hydrogen reactor will then be fed to these two methane reactors. So in the methane reactor, you produce biogas, and the biogas can be stored and then can be cleaned up to produce methane. And that methane, you can also send it to a thermochemical process where methane will be converted to hydrogen, and that is clean and separated into hydrogen. So that is about 220 kg what we are targeting. Now the energy that is produced from the methane reactor can be used to run this whole biohub or the biorefinery. So this is where we can actually either produce methane, use the methane to run this whole plant, and also the surplus methane, about 65% of the methane is then converted into hydrogen. So the first reactor hydrogen that is producing only about 84 kgs of hydrogen, so that's not enough. So we have to go through this methane reactor and then convert the methane to hydrogen using the methane pyrolysis. And this shows that our economics also showed that we can achieve this 220 kgs or 200 kgs of hydrogen per day target, and the price is around $2 to $5 per kg. And wheat straw was found to be the ideal feedstock. And then in a commercial point of view, so a single biohub can produce a hydrogen that is enough to produce the fertilizer urea, because hydrogen can be used as a feedstock for production of the urea, and that can be used as a fertilizer, biofertilizer, biourea on the farms. So the farms can be self-sufficient in producing their own fertilizer rather than going for the inorganic urea production. So this will create an income for the farms, and the farmers can come as a cooperative society and they can also build up this kind of a bio-hub in a centralized facilities. And I thank my sponsors for this project. So it's a federal government project which is funded by the Australian government, and then it was managed by CSIRO and also GRDC, the Grain Research Institute. And my project in industry partners are Made Energy, and also I would like to take any questions if you have, and I would like to thank the organizers for giving me a chance to present my work. Thank you very much.
Okay, thank you very much, Mr. Prasad. And now we are going to discussion session. In Zoom link, in Zoom meeting, the participants can ask through chat room or directly to Mr. Prasad. And also in on-site, if you have any question for Mr. Prasad, just I'm gonna check the chat room. If anyone here having a question. Okay. There are 191 participants in the Zoom meeting. And a couple on site in Bali, Kuta. Oh, in Indonesia? It's okay, yeah. Yeah.
Produksi hidrogen dan metana secara biologi itu memang kita tahu itu di alamnya, dan ini kalau di tadi sempat dalam aspek mekanisme prosesnya itu membutuhkan banyak proses kimiawi dan biologi. Nah, terkait dengan hal ini tentu injeksi jaringan gas alam yang ada di kita di bumi ini begitu banyak dan juga pasti terdegradasi. Nah, dalam ikon seminar internasional ini, apakah dunia istilahnya mentolerir hal-hal yang bersifat yang bersifat nanti bisa merusak lingkungan, tentu ini pasti akan ada impact-nya secara lingkungan. Lalu di sini karena walaupun dia menggunakan bahan baku dari alam, tentu ketersediaan ke depan itu pasti akan sedikit. Nah, ini bagaimana dengan proyeksi ke depan tentang bicara tentang gas alam yang tentu kita ketersediaannya semakin di.
Okay, thank you very much. I'm trying to translate it into English, Mr. Prasad.
Thanks.
Yeah, regarding your material, there are mechanism process using chemical and biological resources. Yeah.
Yes.
And it must be many impacts. Yeah, impact because of using biological and chemical process during the project. The impact on environment. Is there any impact on environment?
Yeah. Yes. Okay.
That the first question, and then there are next question. The natural resources. Yeah, natural resources, of course, will be reducing by time. So, how do you your projection, future projection, something like, the projection about that? Okay, thank you very much.
Okay, so thanks. I think it's a very good question, especially to cover all our participants. And thanks for that question. The first thing we have to understand that any organic waste, if it is left on the field or if it's sent to landfill, it will emit greenhouse gases, right? If you don't do anything, if you leave those organic materials like food waste or agriculture waste, if you don't do anything, if you leave it on the field or you send it to landfill, and if you don't capture that, so what happens? It will emit greenhouse gases. And those are basically, of course, you know what is the impact of these greenhouse gases. But what we are doing now is to utilize these lignocellulosic materials or agricultural residues. Sometimes some farmers will just burn this waste. I think maybe in Indonesia also they'll just burn the wheat straw. They don't do anything because they don't know what to do. So it is a waste there. So they just burn it. And that time also you are emitting greenhouse gases like carbon dioxide or oxides of nitrogen. So what we are saying is that you collect these waste materials and process it in a closed reactors, closed system. So if you see all these bottles, they only produce hydrogen or methane if the inside is anaerobic, means there's no air, so that microbes will only work under anaerobic conditions, means that there should not be any air. So that means that if there's a leak or something, yes, methane is coming out, but if it is leaking, then this process doesn't work. So it has to work only under anaerobic conditions, right? So then what we are doing is we are capturing that, and then we are using it as a energy resource. And then you can replace the natural gas. Now, natural gas is a fossil fuel, and it is limited. And you can replace that with methane and the hydrogen. So we are shifting, slowly we are shifting from use of fossil fuels. By 2050, Australia must have 100% renewables. Either it should be coming from solar or wind or from biogases, right? Now, as I said, gas substitution is much easier, right? You can use the existing infrastructure like gas network, and then what you need to do is just to build the reactors. But you can use the existing infrastructure to move the gas from source of production to source of utilization. So there won't be any net greenhouse gas emissions because it is a CO2 neutral, right? So the biomass, which will anyway emit greenhouse gases, are actually basically converted and stored and reused. And then if you're converting that to hydrogen in the future, so as I show you my final plan, I'm using the energy, everything that is produced on the site. There's no, all the red ones on the bottom is the energy requirements for the plant. And the methane that is produced from the second stage reactor is sufficient to actually take care of all the energy. So there is no fossil fuel electricity grid coming into this power plant or biorefinery, right? Now, the gas is used. Now the digested material, the effluent from this reactor will be used as a fertilizer on the fields. So we are recycling the nutrients present in this material as an organic fertilizer. So now you can see the same wheat straw is giving you hydrogen or methane, and then also the digested material, which can go as a compost or fertilizer. So you have this here, a fertilizer, and then you have the carbon dioxide that can be sold because it's pure. You can also sell it in the market. It has much higher value. It's around $200 per kg of carbon dioxide. So you can sell it in the greenhouses. They can improve their crop production. Then you have the hydrogen. We also get carbon. This is a graphene kind of carbon, and that has $600 value per kg, and that's also revenue. So nothing is wasted in this kind of a closed system, right? So it's a biological process. So the energy requirements are very little. So as you can see, the process is operated at at 37 degrees. This is the temperature requirements for this process. Okay, so yeah.
Okay, thank you. Yeah, it is satisfied. So I can get that there is no net greenhouse gases, yeah, around the world.
Yeah, I mean, yeah, because if you compare, it's basically all the biomass are CO2 neutral. Anything if you produce from biomass is CO2 neutral, right? So it means that you're not actually adding anything, and it is taking care of its own energy needs. So whatever you're producing, you're using on site, and the surplus you are selling it to the market. So that means you are actually reducing the fossil fuel energy consumption for the others. So that's why we can consider it as a net zero.
Yep.
And hydrogen is much better because when you burn hydrogen, you're only producing water. So then that helps in decarbonizing the market.
Okay. Thank you, Mr. Prasad. It's very comprehensive. Okay. I give one opportunity for the participants in Zoom meeting. If you have any question, you can put it on the chat room. But if there is no question, we would like to thanks for everyone here. Thank you very much for Mr. Prasad again for your kindness.
Thank you.
And your presentation. And also all the participants on site in Bali, I would like to say thanks for your attention and also participation. Okay, and we will give to the PIC of this room.
Thank you very much.
Okay.
Thank you very much.
Thank you very much.
See you again.
See you again. Bye-bye. Yeah. Now we move to parallelization. There are seven presenters in this class, and I will give to the time for first presenter, Ms. Normi Muhammad Yahya from University Putra, Malaysia, and the title is Design and Characterization of Potent Inhibitory Peptides Against Bifunctional and Evolutionary Divergent BLEG1 B3 metallobeta lactamase. So, please, the floor is yours.
Thank you very much, Madam Chairperson, and also to the organizing committee of IconSmart. Sorry, I need to remove my mask for a while, or else it's quite difficult for me to breathe. Okay. Thank you very much for the kind invitation. Today I would like to present a little bit on my work on designing and characterization of inhibitory peptides, again, metallobeta-lactamase. If you can move to the next slide, please. Let me introduce you to beta-lactam antibiotics first. It has very wide applications, mainly to treat bacterial infections ranging from pneumonia, urinary tract infections, bronchitis, otitis media, as well as sinusitis. There's a lot more. How do these antibiotics work is basically they lyse the cell of the bacteria by inhibiting some of the cell wall synthesizing process, right? And due to its high effectiveness, they have been widely used, yeah? And also not only because of its high effectiveness, they are low in cost, it's very easy to deliver them with very minimal side effects. And because of that, they have been widely used globally. Next slide, please. As a result of its constant usage, constant usage of the beta-lactam antibiotics, we now see there is a rise of antimicrobial resistance globally. This is really dangerous, and it gives a very negative impact to public health because that would cause the currently used antibiotics to be ineffective. And on the patient side, it will basically prolong their hospital stay, increase the medical cost of the hospital and the patient, and increased mortality rate. So it is projected by 2050, yeah, the impact of antimicrobial resistance would be greatly felt in Asia because of the high population, and as well as it's not very easy to access to have access to medical facilities and therapeutics. So for that purpose, I would like to switch gears a little bit by introducing one of the enzymes that is involved in the resistance of the bacteria. So one way bacteria fight antibiotics and become resistant to antibiotics is by degrading them. Yeah? And the enzyme that is involved in the degradation process is known as beta-lactamase enzyme. So there are two general classes of beta-lactamase, the SBL or serine beta-lactamase and metallo-beta-lactamase, the MBLs. Now among that two, between that two classes of beta-lactamase, the MBL is the most feared one, mainly the B1 and the B3 subclass MBL, mainly because it has a wide degradation spectrum. Okay? Now, most of the inhibitors that are designed and developed, it is targeted to the B1, but the B3, which has a wide spectrum of degradation, however, do not have clinical inhibitors available. So, next slide please, thank you. So I'm going to introduce you the B3 MBL that I'm working on. And this MBL and the B3 MBL that I'm working on is known as Blake-1. Blake-1 MBL is very novel in a sense that it has two activities. It has dual activities. One is to degrade beta-lactam antibiotics, whereby the ampicillin is the preferred substrate, all right? And the other activity is to degrade S-lactylglutathione. Now, we have managed to look at its structure and also its sequence, and we see that that this particular enzyme is not related to any of the currently circulating B3 MBL at the moment. So we are using this as a target for us to design inhibitors. Next slide, please. So we have designed a few peptide inhibitors in silico using docking simulation and analysis. And then we have also synthesized those peptides and then characterized them to see their degree of inhibiting the Blake-1 B3 MBL. And we have obtained two peptides mainly, whereby at only 1 micromolar of concentration, we see that there is a significant inhibition on the enzyme at 68% and 76%. So when we increase the concentration to 10 and 20 micromolar, we see that there is an almost complete inhibition of the enzyme. Next slide, thank you. So we proceeded to look at how low do we need to basically, how low a concentration do we need for the peptides to inhibit the enzyme by 50%. And we have determined the IC50 in this case. For the first peptide, it would be at 0.9 micromolar. And the second peptide, we found out that at 0.5 micromolar, it is already available, able to inhibit the Blake-1 MBL by 50%. All right. So we have also characterized the thermodynamic properties of both of the peptides, how do they interact with the B3 MBL. And we found out that both of the peptides have one binding site similar to the ampicillin antibiotics. It binds to Blake-1 at only one binding site, but it has better affinity and strength compared to ampicillin. Okay. So we proceeded to look at how do these peptides actually inhibit that B3 MBL, Blake-1, by doing a docking analysis, quick docking analysis of the peptide and the protein. And we found out that the first peptide basically binds at the protein at the vicinity of the active site, whereas the second peptide binds exactly at the active site at a very hydrophobic narrow groove. So basically the second peptide has less exposure to the environment, and therefore we postulate that it is less accessible to changes in the environment, and therefore it has better binding strength. Yeah? So both peptides basically block the active site of Blake-1 B3 MBL from being accessed by ampicillin, and therefore that would hamper Blake-1 catalytic function. All right? So as a conclusion, Through in silico analysis, we have managed to design 2 potent peptides that are able to inhibit the activity of BLAK1B3-MBL with slightly improved binding properties. And the peptides were shown to be able to inhibit BLAK1 at very low concentration, and we postulate that they might have bind to BLAK1 near the active site of the enzyme, therefore blocking its catalytic activity. So in the near future, peptides can be utilized as potential therapeutics, yeah, in circumventing the impact of antimicrobial resistance. Right. So with that, I would like to thank my postgraduate students. From my first to my most current postgraduate students who have been involved in this pipeline, from the bioinformatics analysis to the cloning to the crystallization and to the design of the peptides itself, and also to the funding bodies, mainly L'Oreal UNESCO for Women in Science grant and UPM for the grants that have been provided to the postgraduate, as well as fellow ministry and UPM as well that have been providing fellowships to each of my postgraduate. So with that, I would like to thank you for your time and attention. Yeah.
It's okay. Thank you very much for Ms. Normi Muhammad Yahya. And now we move to discussion session. Do you have any question from participants in Zoom meeting or on site? Is there any question? Design and characterization of potent inhibitory peptides. How about the participants in Zoom meeting? 171 participants. Okay. Thank you very much. Okay, thank you for first presenter, Ms. Normi Muhammad Yahya. And now we move to the second presenter, Michael Andreas Lehmann from Samratulangi University with title Determining a Thematic Areas for Healthy Dental Campus in Samratulangi. Then
recording in progress.
Hybrid. Yeah, hybrid from Mr. Negami. Yeah, Negami. Is Mr. Negami here? Mr. Negami. Seiya Negami. I'm sorry. Okay. So for this session, I will close for invited speaker, and now we move to next speaker, Mr. Seiya Negami, and the moderator will be just please, Ms. Moderator, we will change.
Tes tes. Tes tes. Nggak ada berapa? 141.
Okay, ladies and gentlemen, we're about to start this workshop, so please have a nice seat. Good afternoon, everyone. I hope that all participants that come here today and those who attend this workshop online are still full of energy because we have passed so many sessions today, and due to technical problems, we have to postpone the workshop for 1 hour, and now we will start the workshop. Let me present myself. My name is Dewi Sintiari. I am from Universitas Pendidikan Ganesha Singaraja. I'm very happy to see you here and online, and it's an honor for me to be a moderator of this workshop. As all of you probably have read on the schedule, the theme of this workshop is optimization using graphs. Many thanks to Yokohama National University, Japan, for initiating this workshop. Here we already have our speaker from Yokohama, Professor Dr. Seiya Negami. Professor Seiya, welcome in Bali virtually. Can you hear our voice clearly, Professor Seiya?
Yes, I can hear you. Right.
Yeah.
No problem. But as a person, other two person already come here? No, not yet. So Professor Benny informed me that some new link address. So I just check in, but other two person never yet, I think. Make sense? Okay.
Oh, yeah.
So this workshop, yes, there are 3 persons have to speak in this workshop.
Okay, so I'm sorry. So there are some miscommunication. We have 3 speakers, right, from Yokohama. So welcome to all speakers. Before the presentation starts, let me first tell the participants how this workshop will be organized. So first, Professor Seiya Negami will be invited to present the material, and then we will have the 2 other speakers.
Sorry, I will speak Japanese to Professor Kenta Ozeki. Ozeki-kun-san.
Okay, so the 2 other speakers are Professor Atsuhiro Nakamoto, right?
Yes.
Yeah. And Associate Professor Kenta Ozeki. Yeah.
Yeah.
Okay. So first, Professor Seiya. Yeah. Professor Seiya.
All of 3 already exist here. Atsuhiro, can you hear me?
Okay. The 2 other speakers are not yet connected, Professor Seiya.
All right.
So maybe we can start from Professor Seiya while waiting the 2 other speakers to join us online.
Okay, wait a minute. I talked with Professor Kenta.
Oh, yeah.
尾関君聞こえてますか？尾関君聞こえてますか？ 電話。
Okay, we already have Associate Professor Kenta Ozeki here. Welcome, Professor Kenta. Can you hear our voice clearly?
Maybe the Professor Nakamoto never checked up the new address. So someone have to inform him it. So, yeah, so I will begin. Ozeki, 聞いてる?
Yeah, okay, we will try to contact Professor Atsuhiro.
By Ozeki in the Japanese language, so please wait for a minute. Ozeki Nakamoto sensei, 聞こえてる? All right?
はい、大丈夫です。今呼びに行ってます。
Okay, so someone called Professor Nakamoto to come here, so no problem. I can start my talk now.
Okay, right. Okay, thank you, Professor Seiya. Okay, so as I said earlier, we will start by the first speaker, Professor Seiya Negami, and then we'll have the second speaker. So depending whether Professor Atsuhiro will join us or not, we'll see who will be the second speaker. And after the 3 speakers present the material, we'll have the question and answer session, and we'll close the workshop by a little bit of conclusion. Now, allow me to welcome Professor Dr. Seiya Negami to deliver his presentation. But beforehand, please let me to briefly introduce Professor Seiya. So a little bit of academic background of Professor Dr. Seiya Negami. Professor Dr. Seiya Negami is a professor in Yokohama National University in Japan. Professor Seiya was graduated from Tokyo Institute of Technology and is now working in Yokohama National University as Executive Director and Vice President for Education and Information Sciences. Professor Seiya is a mathematician, which is a pioneer of topological graph theory in Japan, and working for reformation of mathematics education. He has written so many papers in many reputable journals, and today we're listening Dr. Seiya, who will tell us about what happens in a very huge network. So Professor Seiya Negami, please you may share your screen.
Right, I try to share my screen. All right, can you see my screen?
Yes, it's visible clearly.
Okay. So I start my slideshow. Well, okay, so thank you very much introduction. And my name is Seiya Negami from speaking from Japan online. So I have first of all I have to apologize to you, our absent in the body. So we actually want to go to Bali and discuss with you directly, but unfortunately many situations didn't allow us to go there. Sorry. And this workshop is presented by YNU Research Center for Topological Graph Theory. And it consists of 3 talks given by these 3 guys. And I am a founder of this research center and was working as a chief before, but a few years ago, I gave that position to Professor Nakamoto, and now Professor Nakamoto is organizing everything on this research center. And also Associate Professor Kenta Ozeki is very strong a mathematician, young mathematician, and he is also a member of this research center. And I think someone here may have already know Kenta, because he has organized some online workshop for students, Samuraturangi University. Okay, I will begin my talk, all right? So question is, today I want to ask such question, that is just the title. What happens in a very huge network? As you know, the computer network grows larger and larger to form a very huge crowd, right? And getting more powerful and giving us comfortable services. However, nothing trouble happens forever, right? I don't know the answer, but I would like to establish a theory to find such a phenomenon in advance, right? Okay. So what is called Ramsey theorem might meet my expectations. This is an area of discrete mathematics to find such phenomenon as follows. Any sufficiently large system contains an unavoidable structure. Theorems with such a statement are called Ramsey type theorem, or simply a Ramsey theorem. To explain this, I will show a very easy Ramsey theorem, which is called a party problem, right? This is a party problem. If there are 6 people together having a party, like this picture, and so maybe I think you can find my name at the bottom of this picture, the Negami. Negami is a Mexican music band. And it consists of 5 people. 1 person is not a member of the Negami. And I don't know the precise meaning of Negami in the Mexican language. This is exactly my name, but I don't know what is this. Anyway, that supports there are 6 people together. Then they include 3 persons who know each other, or 3 persons who don't know each other. Make sense? All right. To make its meaning more clear, I will explain it using a graph theory like this, right? And A, B, C, D, E, F stands for each of 6 persons. And if 2 persons know each other, then we draw a red line between them. And on the other hand, if they don't know each other, we draw a blue line. In this picture, and Mr. A and knows D and also knows F, but he doesn't know where B, C, and E. Make sense? So we can draw such a graph, right? Okay, so suppose look at Mr. A, the top guys, and so you can find 5 lines joined to the other person, other 5 persons. And so in this case, Mr. A has 3 friends, and the 2 other guys he doesn't know. And in generally, so from one person, 5 lines goes outside, right? And these 5 lines, these 5 lines colored by the red or blue. So more than half edges must have the same color. For example, a blue or red. In this case, in this picture, there are 3 lines. And we focus on the 3 persons, B, C, E in this case, and consider the tetrahedron having the 4 vertices. All right, I'm sorry, something strange. Okay, again, so look at the 4 persons, A, B, C, E. Okay, so this is to make a tetrahedron, and look at such tetrahedron. So I will show you that tetrahedron, the right side, like that. If the bottom triangle, base triangle, has a blue line, for example, between E and C, we can find a blue triangle ACE. So if there is a blue line between BC or a blue line between BE, and in any case, we can find blue triangles. But if there is not such a blue triangles, so the base triangle has only red edges. In this case, we can find red triangles. So we can conclude that there exists either a red triangle or a blue triangle. Make sense? All right. So, the red triangle, of course, correspond to 3 persons who knows each other, right? And the blue triangle correspond to the 3 persons who don't know each other, right? So these arguments, conclude some party problem. Okay. So if he state the party problem in the terminology of graph theory, we can say that the complete graph K6, something happened. The complete graph K6 with the color edges colored by red and blue like that, so arbitrary, contains either a red triangle or a blue triangle. Makes sense? And for example, this picture is show 1H never yet colored by any colors, right? If we add along the horizontal line, we color just blue, so we can find many blue triangles. If color the edge vertical line, vertical edge by red, so also we can find red triangles. Okay. So graphically, a red triangle can be regarded as a complete graph of over the 3 vertices. We denote it as K3. And so a red triangle can be called a red K3. On the other hand, the blue triangle can be, say, or the blue K3, right? So, and we call these triangles just monochromatic triangle. Monochromatic means just colored by only one color, right? So red triangle colored only red, and the blue triangle colored only blue. So in any case, red triangle, the blue triangle, we can call them just monochromatic triangles. Okay. So we can say if there is 5 or more vertices and joined by the blue and the red edges arbitrarily, then always we can find a monochromatic triangle. Okay. So I have a question, just a problem for exercise. Complete graph K6 with edges colored by red and blue arbitrarily contains at least 2 monochromatic triangles. We have already found one monochromatic triangle. So please find another one, right? But this is just an exercise for beginners. So I recommend you consider this problem after our workshop. Okay. So, well, I want to talk about the huge system. Yeah. Now we're discussing about only a very small system consisting of only 6 persons. So now we consider a very, very big system, right? So the party probably can be generalized into this theorem, right? Given any 2 natural numbers, m and n, then there exists a natural number k, which is a function of 2 parameters, m and n, such that a complete graph kr, which means which have r vertices, so in many vertices, with edges colored by red and blue arbitrarily, it contains either a red km or a blue kn. So instead of a triangle, just now include a very big complete graph. It's a monochromatic complete graph, or red or blue, right? So very roughly speaking, sufficiently large complete graph colored by 2 colors always contain enough big monochromatic complete graph. For example, this picture showed maybe the complete graph of 28 vertices, and its edges colored by red and blues. And if you choose vertices arbitrarily, suitably, then you can find this complete graph consisting of only red edges or blue edges, right? So, but I don't know which one occurs. Well, minimum value of this number R with the 2 parameters, m and n, is called Ramsey number. And for example, Ramsey number of 3 and 3, that is R33, is equal to 6 by our previous argument of a party problem. It is hardly possible to determine the precise value of the Ramsey numbers for general parameters. However, small cases has been already determined as this table. I get this table from Wikipedia, but I don't know the detail of this history. Please check it up by yourself if you take your interest in how this table is determined. Anyway, the Ramsey number is a very large number in general, but it is a finite number. So thus we can find the sufficiently large complete graph colored by 2 colors always contain an enough big monochromatic complete graph, right? That this is the unavoidable structure. And now we have just discussed the Ramsey number for 2 colors. However, there has been known the Ramsey number for 3 or more colors, right? To understand this situation, look at the sky at night. You can see in a lot of stars. There exist 100 trillion stars in the universe, a very, very, very huge number of stars, right? So well, make the complete graph over the 100 trillion stars. Of course, we can we cannot do that practically. But just do it in imaginary in your brain. So, and assign 3 colors, red, blue, and yellow to its edges according to the following rule, right? Red, if 2 stars are moving away from each other, so we assign a red to the edge and joining to these stars. If 2 stars are approaching to each other, we assign blue to the color between them. And otherwise, that is 2 stars keep their distance, keep the distance, not approach, not going away. So if we assign yellow to its the edges between them, right? So what's happened? So by Ramsey's theorem, we can conclude that there is a very, very big monochromatic complete graph consists of the stars, right? It's totally red or totally blue or totally yellow. These situations corresponding explosion or shrink or rotating, right? Such phenomenon happens in many, many places in the universe, but we can conclude such situation, existence of such situation, you know, but we never calculate anything, and also never try to solve the differential equation that physicists use. And that is the point. This is a mathematical power, right? So I like power and force. In particular, there exists a huge number of stars. They are just correspond to explosion or shrinking or rotating, right? So just I love Star Wars. So anyway, I want to introduce my theorem, my Ramsey theorem. I proved the 1998, and I proved a Ramsey type theorem for the spatial graph. It's slightly difficult to understand, but a statement like that. Okay, given a not a ring on a spatial graph K, a knot is just a closed curve drawn in a 3 space, and the link is a collection of knot. Collection of a simple closed curve in a space, and the spatial graph is just a graph drawn in a 3 space, like a frame of polyhedron, right? So given such things, there exists a natural number R. It should be called the Ramsey number for K, such that any spatial rectilinear embedding of the complete graph with R vertices contain a subdivision of K. So it might be difficult to understand this statement precisely. So explain it very, very roughly. Please imagine a sufficiently large complete in graph, the 3 space like this picture, right? This is a complete graph. There are many huge number of vertices plotted and joined by line segments and to make the complete graph, right? And imagine the focus. Imagine the frame of the cube just in your mind, okay? And then we can find the frame of cube in this very, very huge complete graph. It's contain a frame of cube, but partially subdivided, okay? The edge is not a straight line, just for example, one edge is consists of 2 edges of the complete graph. So I try to deform the complete graph itself to destroy such cube, changing the situation, relative position of edge and ups and down, change ups and down. So such a frame of cube destroyed. The cube will not be not in a cube anymore. Then so it disappears. But we can find another frame of cube in some place, right? This is my theorem. So it's very roughly speaking, very big complete graph, drawn in 3 space. So any drawing contains cube, frame of cube, right? This is my theorem. Okay, so how about neuron? So now imagine our brain. Our brain consists of a lot of neurons, right? But I think neuron is impersonal, and basically everyone the same, all the same. But our brain have many parts, and many parts it's correspond to different functions, vision and hearing, and so on. So even if the neuron itself are the same one, why the brain so divided into the many parts correspond to different function? I think it's very near to the Ramsey phenomenon. So that is a mystery of life or a mathematical fact. Okay, so another thing. Recently, artificial intelligence, AI, has been more popular. In particular, deep learning works well in many areas in our society. And at the present, what happened inside of the deep learning is unknown. Just we know it works well. So the inside unknown. I imagine something special will happen inside a very large network of deep learning. It's very similar to the Ramsey theorem. So well, finally, I talk about my dream. Something wonderful or something bad would happen in a very large, huge network, and a mathematician will prove it someday in the far future. This is my dream. That's all. Thank you. That's the end. Okay. Can Kenta give a lecture?
All right. Okay, thank you very much to Professor Saya Negami for the interesting talk. So now we are welcoming Associate Professor Kenta Ozeki, who will talk about, yeah.
I'm sorry, the second one is Nakamoto, please. I'm very sorry.
Okay, so I'm sorry for, okay, so Professor Atsuhiro Nakamoto, are you connected with us? Can you hear our voice?
Yes, I'm Nakamoto.
Okay, good. Okay, so welcome Professor Atsuhiro in Bali, virtually. We are going to listen to your presentation now. So as written on the schedule, you are going to talk about flip distance of triangulation on surfaces, right?
Yes.
Okay. So Professor Atsuhiro, you may share your screen.
Yes. Sorry, can you see?
Yes.
So, thank you for the introduction. My name is Atsuhiro Nakamoto. Okay, I'd like to talk about flip distance of triangulation on surfaces. Okay, First of all, I would like to thank the organizer to invite this workshop on optimization using graphs. Okay, I really wanted to visit Bali, but now I'm in Japan. It is very pity. Okay. So I will start my talk. Okay. Is this presentation is correct? Okay.
Yeah, we can see that the title of the slide is triangulation on surfaces.
Okay. Yes. Okay. Yes. So a triangulation G on surface is a map of unraveled simple graph on the surface such that each face is bounded by a cycle of length 3. Okay, so this is an example of triangulation on the sphere, which is isomorphic to the octahedron.
Excuse me?
Yes?
I think that you have a long presentation mode.
Okay, so I should exchange display like this.
It seems
this correct? Okay?
Yes, it looks fine.
Yes.
Thanks.
Okay, thank you. So, yeah, this is another example of triangulation on the torus. From this rectangle, okay. So from this rectangle, we have a torus by identifying red segments and blue segments respectively. Then we get a torus, okay? This is a triangulation on the torus whose graph is K7, okay? So when we embed the graph on the sphere, then the number of vertices minus the number of edges plus the number of faces equals 2. We have, which is called Euler's formula, okay? And we substitute this relation for triangulation. 2 times the number of edges equals 3 times the number of faces. Okay, eliminating f from these 2 equations, we get this. Okay, the number of edges equals 3 times the number of vertices minus 6. Okay, this means if we fix the number of vertices in triangulation, then the number of edges is automatically determined. Okay. Moreover, by this relation, the number of faces is also automatically determined by V. Okay, please remember this. Okay. So for the torus, we have a similar fact, but today's talk, we concentrate only triangulation on the sphere, so we omit the detail for the torus. Okay. So I'd like to introduce elementary operation for triangulation called diagonal flip. Okay. So a diagonal flip, diagonal flip is to switch the diagonal to move it to another diagonal like this. Okay. But if the resulting graph is not simple, we don't apply this operation. Okay, this means we would like to keep the simpleness of graph always. Okay. And triangulation G and G prime are said to be equivalent and denoted by this symbol if they can be transformed into each other by diagonal flips. Okay. The flip distance, this terminology is appeared in my the title of the talk. Okay, the flip distance of G and G prime is the minimum number of diagonal flips needed to transform G and G prime, and denoted by this G prime. So we'd like to introduce a classical result called Wagner's theorem. Okay. Wagner's theorem states that any two triangulation G and G prime on the sphere with the same number of vertices are equivalent to each other. Okay, so these are two triangulation on the sphere with 6 vertices. So believing this theorem, they can be transformed into each other. Okay, we do. So we first, sorry. As we mentioned before, if we fix the number of vertices like this, then the number of edges and the number of faces are automatically determined. So if we assume this and this have the same number of vertices, then they also have the same number of edges and same number of faces like this. Okay, okay, so we have a demonstration like this. Okay, so okay, so we move this edge like this. Okay, move this edge like this. Okay, so moving the position of these 3 vertices by homeomorphism on the sphere, we get this. So those 2 triangulation can be transformed into each other. Okay. So Wagner's theorem has been generalized to non-spherical surfaces, and many YNU people contributed to such a topic. Okay. But today we concentrate only triangulation on the sphere and consider flip distance of them. Okay. Okay, we'd like to introduce Wagner's proof. Consider a triangulation on the sphere, and we focus on top vertex V. Okay, and we consider whether this edge can be flipped like this. Okay, if we can flip this edge, then we proceed. Okay, so suppose it is forbidden, then we have such an edge. Okay, in this case, if we flip this edge to here, then we have multiple edges. Okay. However, by planarity, in this case, we have such an edge. We don't have such edge, so we can flip like this. Okay, therefore, now we find that at least one of this edge and this edge are flippable. So repeating these procedures, we get this. Okay, so we can always decrease the degree of V. Okay, so we get this. Okay, repeating these procedures. Okay, and now we focus on this part and consider the degree of this. Okay, then we repeat as before. Then we get this, and we eventually have such a structure. Okay, we call this the standard form of spherical triangulation. So Wagner's method is as follows. Every triangulation can be transformed into the standard form by diagonal flips. Okay, so any 2 triangulations can be transformed into each other via the standard form. Okay, so this finishes the proof of Wagner's theorem. Okay, using Wagner's algorithm, let's estimate the flip distance of G and delta N. Okay, so from this to this, the leftmost one and the next one, okay, we had at most N-1 edge here, and in this triangulation, this vertex has degree 3. Okay, difference is n-4. So we needed at most n-4 from this one to this. Okay, so the next, now we have at most n-2 edge here, and here we have 3 edge here. So the difference is n-5. So repeating this summation, and we got this order n square. So Wagner's proof implicitly shows the flip distance of any two triangulation G and G prime on the sphere with n vertices is order n square. Okay, is it best possible? We'd like to consider this. Okay. So now we consider two triangulation which need many flips. Okay. So for this question, there exist two n vertex triangulation G and G prime whose flip distance is at least 2n-15. Okay. We can prove this one very easily, so I'd like to mention it. And very recently, this 2n minus constant has been improved to this. Okay, but a little bit complicated, so we mention this one. Okay. Consider G, which is a triangulation with maximum degree 6. Okay, such a triangulation can be easily constructed. Okay, and another one is the standard form. Okay, so in G, every vertex of G has degree at most 6, but in G prime, there are two vertices with very large degree. Okay, this and this. Okay, this is the difference. And consider the flip distance of this G and G prime. Okay. And we consider effect of a single diagonal flip to a triangulation. Okay, in this case, the degree of U and the degree of B increased by 1 respectively. Okay, so let's consider the flip distance of G and G prime. Okay, okay. Since each vertex in G has a degree at most 6, okay, so these two vertices become this and this. We may suppose this. Okay. So let's consider this. If this x, this x and y are not adjacent, then degree x and degree y might be increased simultaneously. Okay, but if degree x and degree y are increased simultaneously, then in the resulting graph, x and y are adjacent. Okay, and if x, y are adjacent, then we cannot add edge x, y anymore. So at most one of degree x and degree y is increased by any single diagonal flip. Okay, therefore, we have to increase the degree of x and degree y almost separately. So the flip distance of this G and this G prime is at least these numbers. Okay, so the flip distance is at least 2n minus constant. Okay, so so let's consider upper bound. We already know there are lower bound with the lower bound is linear. So now we mention the upper bound is also linear. Okay, so this is our result. let G and G prime be n vertex triangulation on the sphere, then the flip distance is at most 6n. Okay. So upper bound is 6n and lower bound and 2n. So yeah, we want to know the coefficient, real coefficient. Okay, so a linear bound was first given by Komuro in 1997, but our result gives a much better explanation, and moreover, it is easily understood. So we'd like to mention this one. Okay. And after that, these people improved this 6n to 5.2n, and very recently, these people improved this 5.2n to 5n. Okay, I think this is currently the best bound. Okay, so but we'd like to introduce this one, this result. Okay. So the method is to use Hamiltonian triangulation. So our purpose is to prove if G and G prime are n vertex triangulation on the sphere, then the flip distance is at most 6n minus constant. Okay. So in order to prove this, we use this lemma. Okay. Let G and G prime be n vertex Hamiltonian triangulation on the sphere. Then the flip distance of G and G prime is at most 4n. Okay, if we compare this and this, so in this lemma, if we assume Hamiltonian triangulation, then the flip distance is decreased. Okay, from 6n to 4n. Okay, so we prove this. So let G be a triangulation on the sphere with a Hamilton cycle C, like this. Okay. Hamilton cycle is the cycle passing through each vertex exactly once. Okay. Then we can see that the interior and exterior of C are maximal outer plane graphs like this. Okay. So we have this. Okay, so our idea is to decompose Hamiltonian triangulation into two maximal outer plane graphs. Okay, so now G has a Hamilton cycle C, so G has two spanning maximal outer plane graphs H1 and H2 sharing C. Okay. And our idea is to apply a diagonal flip in H1 or H2, okay? But we have to be careful to consider this edge, okay? So, of course, this edge is flippable in H1 to be able to put this one here, okay? However, the edge 2,4 already here, so flipping this edge is possible in H1. However, it is impossible in G because of edge collision of this, this and this. Okay, so we have to be careful. Okay, so we focus on this vertex. So H2 is also a maximal outer plane graph. So this has a vertex of degree 2. Okay, so we can find no inner edge incident to this. Okay, because this has a vertex of degree 2 in H2. Okay, therefore we can do this. Flipping this and flipping this and so on, okay? So we can increase the vertex 1 like this, okay, one by one, okay? So now we have, this edge has at least the degree of this vertex has at least 3, and here we have the degree n-1 here. Okay, so the difference is at most n-1. So we needed at most n-1 flips from these to this. Okay, now our graph is obtained from this one and this one by pasting them along C. Okay, so now we transform this. Okay, and we focus on this part, this vertex. Okay, we have no inner edge incident to this vertex too, so we can do that. Okay, flip this edge to here and flip this edge to here and so on. We can increase the vertex, the degree of vertex 2 to n-1 here. Okay, so we need at most n- constant flips. Therefore, no. Okay, now our graph is obtained from this one and this one by pasting them along C. Okay, what is the resulting graph? Okay. Our graph is as follows. Vertex 1 has degree n-1 and vertex 2 has degree n-1 and they are adjacent. Okay, so our graph is nothing but the standard form of spherical triangulation like this. Okay, therefore, if G is n-vertex Hamiltonian triangulation, then the flip distance of G and this one, the standard form, is at most 2n minus constant. This means for any two n-vertex triangulation G and G prime on the sphere, the flip distance is at most 4n minus constant. Okay. So, let's prove our main result. Okay. Let G and G prime be n-vertex triangulation, G and G prime. Okay. Suppose G can be transformed into a Hamiltonian one, and G prime is also transformed into G prime Hamiltonian one. Okay. By the lemma, okay, this Hamiltonian triangulation and Hamiltonian triangulation can be transformed into each other by at most 4n diagonal flips via the standard form. Okay, so we have to consider how can we transform G into a Hamiltonian triangulation. Okay. So for this purpose, we use this Tato result. Okay. Every four connected planar graph is Hamiltonian. Okay. So applying at most n-1 flips, we can prove G can be transformed into four connected one. Okay. We omit the proof, but so by using this extra diagonal flips, we get 6n diagonal flips are sufficient. Okay, this is a proof. Okay, we already mentioned someone improved this 6n to 5.2n, but they actually improved this n-1 flips to this many flips. Okay, by this improvement, they improved 6n to 5.2n. And yeah, it is best possible if we try to transform G into a four connected one. Okay, they insisted. Okay. Moreover, they improved this flip to this. Okay, but they gave up to transform G into four connected one. They didn't use this one, and they count the number of flips to transform G into just a Hamiltonian one. Okay, so by this improvement, they got this result, which is currently the best bound, I think. Okay, so I'd like to give conclusion for the spherical case. Okay. Wagner first proved that any two n-vertex triangulations G and G prime on the sphere are equivalent. And his algorithm suggests the flip distance is of order n square. Okay. We currently know the flip distance for any two triangulation G and G prime on the sphere at most 5n minus constant, but we can construct G and G prime with flip distance is at least this many diagonal flips. Okay, so we want to know the exact coefficient. Okay, I think it is difficult. If we establish an argument without the standard form, we will be able to get a better bound for the flip distance of G and G prime. Okay. So that's all. Thank you very much.
Okay. Thank you very much to Professor Atsuhiro Nakamoto for a very nice talk on the flip distance of triangulation on surfaces. Okay, before we go to the third speaker, I'd like to tell the participants who want to ask questions. So for those who join us on the Zoom meeting, you can start to write your question via the chat room. Please tell your name and your affiliation and your question, and then I will help to read the question on the question and answer session. So now we are welcoming our third speaker from Yokohama, Associate Professor Kenta Ozeki, who will talk about a list orientation of a graph. Professor Kenta, can you hear us?
Yes, I can hear you.
Yeah. Good afternoon, Professor Kenta. So you may share your screen.
Sure. First, Professor Nakamoto, could you close yours?
I don't know. Okay.
Yes. Can you see the slide?
Yes, we can see it clearly.
Okay, good. Can I begin?
Yeah, you can start, Professor Kenta.
Okay, thank you. Thank you for the introduction, and thank you so much for organizing that nice workshop. And I'm so happy to give a talk in this workshop. Yeah, fortunately, I also join in online, and hope I can visit your place in future. But yeah, I'd like to give a talk about my recent research on list orientation of a graph. Sorry, this should be removed. And draw. One team wins and one team loses, right? But I am not interested in which team is the strongest, but I'd like to see some result. Okay, before going to the matches, we first ask each team how many wins do they want? So one team may say that they want to win all games. Yeah, that's possible. Or some team may say that they want to win at least half games. So in this case, at least 3 games they want to win. And like that, each team says something which is the number of wins they want to have. So I'm interested in that under these constraints, whether there is a result of the tournament which meets all of the requirements. So in this case, we have a result like this, which meets all of the requirements. So like team A wins all games as required. Team B wins 3 games, which is as required by team B, and so on. So like this, I'm interested in whether there is a result meeting all of the requirements. So sorry for that. Okay, so, but we also think the little bit strange situations where each team may say that the strange, some numbers, which is the number of wins they want, but sometimes they may be strange. Okay, team A may say that they want to win 3, 4, 5 games. That might be possible. But some team may say that non-consecutive numbers. In this case, team B says that they want to win in 2, 3, or 5 games. They do not want to win exactly 4 games. Like that, each team says some numbers which may not be consecutive. But under this situation, I'm interested in whether there is a result which meets all of the requirements. Like that. So in this case, there is. Actually, this result meets all of the requirements. Team A wants 5 games. Team B wants 3 games, and so on. This seems so strange because each team may want to win as many games as possible. So no team says that they want to win in 0, 1, or 4 games. I don't know why they do not want to win in 3 or 2 games, or 5 games. But this is a mathematical puzzle. So even in such natural situations, we'd like to find whether there is a result of tournament which meets all of the requirements. So this is the task. And okay, so this is related to the main target. So I now check this sum. So I should note that the sum of the wants is exactly the number of matches, of course. And in this case, the sum is equal to 6 to 2, so which is 15, yes. Okay, so I give a statement, precise statement of this case. So find the smallest integer fn satisfying these conditions. So we have a round robin tournament by n teams. And each team says fn numbers in the numbers between 0 to n minus 1 as a possible number of wins. And our task is to find the result meeting all teams' requirements. Of course, each team says many numbers. It is more likely we can find the result meeting all of the requirements. So the problem is that how many teams they need to say, okay, each team needs to say to find or to find the result meeting all requirements always. This is a problem, and in our researches, we show that this number is between half of men and 2/3 of men. But we could not find exact value for these questions. But we conjecture that the lower bound should be equal. I don't know. Also, I will explain that later, but even in the case where n equals 6, we have no result. We do not have an exact value. So even in this situation, we now know that if each team says only 3 numbers, there are some bad choices, which means that there are some numbers of each team where we have no result meeting all of the requirements. But we don't know whether number 4 is enough, which means that we don't know whether if each team says 4 numbers, whether we can always find a result meeting all requirements. That's an open problem. So this comes from just a puzzle, but we would like to think this puzzle in a graph theory point of view. So then we call it L orientation. I'd like to define that meaning. So we are interested in the graph, so we consider the graph theory problem. And orientation of a graph means that the operation to obtain a direction to each edges. So we are given an undirected graph like this, and then we give a direction to each edge. This operation is called orientation. So in the world of a round trip tournament, it means that each vertex corresponds to each team, and each edge corresponds to one game. As I wrote on the right top, if one team wants the game against the opponent, then we put the directions from a team who wants to a team who lost. So that orientation means that to get the result of the games. And the number of wins of each team correspond to the out degree of each vertex. So the out degree means that the number of edges outgoing from that vertex. So for example, in this vertex, there are 2 edges leaving from that vertex, so the out degree is equal to 2. But this vertex has only 1 edges outgoing from that vertex, so the out degree is equal to 1. Like that, the out degree corresponds to the number of wins of that team. And we consider the problem in the puzzle I already introduced. So for each vertex, there is a set of numbers which correspond to the numbers which they want to mean. So each vertex have a list of the numbers. For example, this vertex has a number J1, this vertex has number J2, like so on. With the list given, we consider an L orientation of the graph, which is an orientation such that the R degree is in the list. So in this example, from a given graph with a given list, we have this orientation. So you see that this vertex has a degree 2, which is in the list. This vertex has a degree 1, which is in the list. So all vertices have an R degree, which is contained in the list. So this orientation is said to be an L orientation of the graph. So to obtain, in the puzzle I explained, to obtain a result meeting all of the requirements means an L orientation of a corresponding graph. So in the terminology of graph theory, we want to consider an L orientation of a given graph together with a given list. Okay, I begin with some puzzle, but this problem is related to some important classical topics in graph theories. In the graph theory terminology, the orientation corresponds to correspond to a linkage problem. So if you want to move some items in the network to some vertices, that such a problem, some of the such problem can be translated into some orientation problem. So there are many works on orientation in graph theory, and using such a result, we have we can solve an L orientation problem for some special cases. For example, if the list, all of the list is just an interval like this, from 1 to 3, from 0 to 1, and so on. If all lists are intervals, this problem can be solved in polynomial time. So we have a good algorithm to decide whether there is an L orientation from a given graph and given lists. But in the general case, it is known that the problem is NP complete, so it must be hard, tough problem. And interestingly, if the list have some modular conditions like 0369 or 159, like that, if it satisfies the modular condition, then the problem, L orientation problem, is related to K-flow conjecture. It's a big conjecture in graph theory. So like that, this problem is related to the important area of graph theory. But so we consider this problem, L orientation problem, looking at such a relation to such important topics in graph theory. And also we'd like to think how to find an L orientation in a given graph. And especially in my talk, I will focus on K-regular graphs. So each vertex has the same degree K. And if the list is huge enough compared with K, then we'd like to find an L orientation. We consider this problem, but to do that, I give us some exercise related to that. So there are 3 examples, 3 graphs with some lists. So those does not have an L orientation. But the problem is that why they do not have the L orientation. And those reasons will give us some future for this problem. So I'd like to explain the reason why they do not have L orientation. So the first problem, you may think by yourself like that. So the first problem is with this graph with the list 0, 1 for all buses. And the second one is just a C5 with the list 0, 2 for all buses. The third one is the complete graph of order 5 with this list. If you are interested in, then please think by yourself that one, but I'd like to explain this. So the first one is a little bit easy. So this all buses has a list 0, 1. So in some sense, if you want to find an L orientation, the number, the out degree can be only the small numbers, only at most 1. That's a problem. If you try, you can soon find that the edge cannot have a direction because of the out degree constraints. So in this case, to satisfy the out degree at most 1, you can give a direction to only 6 edges. But there are 9 edges. There are too many edges compared with out degree conditions. So too many edges compared with the out degrees, which is required from the list. That's a problem for the first case. And more generally, we see that some problem happens for general k-regular graphs. So let it be a k-regular graph where k is odd. And we put this list to all buses. Then there is no L orientations. So the problem is that now in the undirected graph G, each vertex has degree k. So there are k edges to incident to each vertex. But from the list, in the L orientation, if it exists, it can have strictly less than half of k edges outgoing from that vertex. So there are too many edges. So more precisely, I can explain like that. So if there is an L orientation, then we can calculate like this. So first, first we have this equality. So the number of edges is the sum of our degree. Both each edge has a one direction. So the number of edges in the graph is the sum of the out degrees. But each out degree is at most this number. So the sum is bounded with this. But using the handshaking lemmas, both it is smaller than the number of edges. So we have a contradiction. The number of edges is less than number of edges. That's a contradiction. So we conclude that this graph G has no L orientation. So in this case, the size of the list is this value, k plus 1, half of k plus 1. Even with this huge number of lists, there is a bad example, some example which doesn't have an L orientation. So that's the issue. So we may obtain some result, assuming a larger list give us an L orientation always. And we prove that this is the case for bipartite graph. So for bipartite k-regular graph, if you give a list of this huge size, we can always find an error orientation. This is only for bipartite graph, but we have a positive result. So I do not explain, sorry, I have no time to explain the detail of this proof, but this is only for bipartite graph, unfortunately, and for non-bipartite graphs, that size is not enough, which I will explain next. So to explain the reason why the size is not enough, we should think the two exercises. So the second exercise is the case C5 with the list 02. Maybe it's the reason is very easy. So because of the restriction of the our degree, the direction of the edge must alternate along the cycles. To keep the degree 2, if we put this direction, then the next, the edge must have the direction like this, but then, and so on. So you have alternative directions along the edges, but this is an odd cycle, so there are no way to complete. This concludes there is no error orientation of this graph. Okay, this is the reason, but I give another reason for another explanation why this doesn't have an error orientation using this inequality which appeared before. So the number of total edges is equal to the degree sum. But in this example, the number of edges is 5. This is odd numbers, of course. But if there is an error orientation with this list, all our degrees must be even, 0 or 2 must be even. So in this equality, the left is odd, while the right must be even, which is a contradiction. So because of the parity constraint, there is no error orientation with this example. And these parity conditions can be generalized for other cases. So suppose a k-regular graph with k even, but the number of edges is odd. Take such a graph and put this list to all bushes, taking all possible even numbers. We put this list to all bushes, and then by the same reason as above, there is no error orientation of the graph by the parity problem. And the list has a side, this is the one. And this value is slightly larger than the previous one. So even if we put such a huge set of numbers to each vertex, there still no error orientation of the graph. I should notice that such graph, there is no bipartite graph satisfying these conditions. So this doesn't conflict our previous theorem, but if we think a non-bipartite graph, we need to think these parity conditions. And there are another example which is more strange, but actually there is. The third example, which doesn't have an error orientation, I explain the reason. So suppose there is an error orientation of this graph, and suppose this vertex has R degree 4. So in this case, this vertex has degree 4 and R degree 4, which means that all edges incident to this vertex must be outgoing from that vertex. So we can observe that other vertices cannot have degree out degree 4 because one edge is incoming already. So this vertex cannot have out degree 4. And of course, all others cannot have out degree 4. So each vertex, each other vertices, all of the other vertices can have out degree 0 or 1. But then there are too many edges remains to have the out degree 0 or 1. So that's a problem. So the list seems strange, but in this situation, if you take a huge out degree for some vertices, we have too many edges remain. That's an issue. We can generalize this result like that. So if we take a complete graph of order k plus 1, where k is even, and if you take this list to all vertices, there is no error orientation. So the point is that we have a value k together with small numbers. So the list seems strange, but this list has size that number, which is the same as the previous example, but there is no error orientations. And yeah, I only explained the case of a complete graph, but there are more examples. So anyway, we have some example with this size, but does not have a error orientation. So we assume a little bit more, and this is our main conjectures. So any graph, any k-regular graph, if you put a list of this huge size, that graph always have a error orientation. That's our conjecture. And studied many cases, but we couldn't solve this. This conjecture is open even for complete graphs. So I think this is natural conjectures question, but it's still open. Maybe I need to. So we have some result about that. So there are some special cases for that. So we solve some special cases that yeah, unfortunately this is open question, open problems. And even in the case of complete graph, this is unsolved. So what we obtain for complete graph is a case where each vertex has this huge list. So and assuming this, and assuming each vertex have such a huge number of lists, then we always find an error orientation. Or even for these conjectures, if all lists are the same, then we show that there is an error orientation. But generally, that conjecture remains. So I explain some possible open problems which can be tried. In some sense, I introduce some reasonable problems which may be able to obtain the answers. So actually, the next open case is case 6 with the list size 4. But even in that case, I have no answer to that. The list size 4, I don't know whether the list size 4 is enough or not. So this is still open. I have no idea how to attack that. As I explained, if the list is same for all vertices, we could prove there is always error orientation. But for the next case, we don't know what happens if there are two types of list. We may think following the proof of this result, but it might be difficult, I don't know. Or you may consider the problem fixing the list. But from some technical reason, this list seems tough. The list having the small numbers and also big numbers, or something similar to this. That list seems tough concerning some to prove the general cases. So it was trying to the case with this list or similar lists with this. So focusing the fixing some particular lists, it is worth trying to as a step to attack the general cases. So I propose those questions to obtain the general result. So that might be interesting and important step for the conjectures. I think I prepared some results, but I think it's almost a time to end. Maybe I break the time restriction. Sorry about that. So I like to stop my talk with those open problems, and hope you are interested in and try to them. And thank you for listening.
Okay, thank you so much for Professor Kanta for the interesting talk. So I think there are more slides. So for those who are interested in reading more slides, maybe you can contact Professor Kanta to get the slide probably. Okay, before we go to the question and answer session, let us first thank the three speakers, Professor Sayar, Professor Atsuhiro, and Professor Kenta by giving an applause. Okay, so now we are going to do the question and answer session. For those who join us online, you may write your question on the chat room, or you can ask directly to the three speakers, or maybe there are any question from the participants who are here on site. Please. Yes, please. Please introduce your name and the university.
Thank you. Good afternoon. Thank you for the chance. I'm from Ganesha University. My question is, sorry if I mistake to call the theory, the name of the theory. I forgot the name. My question is for the speaker one. I have something interesting with the topic of the Ramsey theorem for the universe. I'm a physicist. I study about gravitation, and that's if I study about Einstein gravitation, there is the application in cosmology. Cosmology is one modeling of the universe. Okay, when we discuss about Einstein gravity, we use the Riemann geometry with the Levi-Civita connection, and if we describe the dynamic of the universe by the Einstein field equation, and we have to solve this equation, and the solving of this equation, we get the model of the universe. Okay, my question is, maybe that's related about that theory. And if it's related, what is the correlation need? And what the compare it with R in there, the function R in there? I think that's something in there. I think that that's my question. Thank you, and thank you for the chance.
Okay, I should answer her. So, but a difficult question. And she are studying about Riemann geometry. But in a universe, there are many systems of the planets. And it should be making some stereographical structures. For example, and recently I read some book. The title is The Book Before We Should Read. I said, so sorry. The title is just Japanese, just a book that should be read. I read this before we meet alien. So we have, our solar system has only one sun, but this is a very rare case. So usually sun system, right, consists of many suns together. And the surrounding the planets, many planets going around. Such system has some spherical relationship. Can you understand by the using Riemann geometry? So I said, I said in my talk, I never calculate anything and also not try to solve differential equations. So in the space, in the universe, in the world, there are many things, combinatorial structures cannot analyze in such differential methods. So I'm just talking about my dreams, so not so mathematical. So, but I think answer to your question, I think enough. Thank you.
Okay, thank you, Professor Seiya, for the answer. Is there any other question from the participants? Or maybe I have one. So I have two actually. So my first question is for Professor Seiya for the first talk. So you talk about Ramsey theorem for complete graphs, but as we know that in the real world, not all huge network can be represented using complete graphs because there might be many edges missing. Are you aware of any research or any result about graphs that come from a huge network, from the real networks? And is there any study on some version, maybe different version of Ramsey theorem on this type of graphs?
Sorry, I never I slow the question to the Kenta. Kenta knows many things about the Ramsey theorem. I'm basically the geometers, not combinatorians people. So I don't know the details of the Ramsey theorem. Please answer, Kenta. Sorry.
Neither to me, I'm not the expert of the Ramsey theory, but there are many researches for not only complete graph, but also many types of graphs. So, I think that nobody considers the relation to the real network. Just in mathematics, they study to find the Ramsey number for many graphs. So if you check some, for example, some survey papers, you may find something interesting to you. I'm sorry, I don't know so much, but I just can say that there is a good survey on that.
Okay, thank you so much for the answer, Professor Kenta. I again welcome the participants if you have any question. Okay, if there's no question, let me ask one more, because we have more than 100 participants online and there are some participants who are still here it's 5:35 in Balinese time now, but they are still very enthusiastic to attend this workshop. So probably from these 100 participants, I think there are many lecturers from mathematics or natural sciences, or maybe from computer sciences, or maybe there are some undergraduate students. And among the lecturers, I think most of us teach in undergraduate programs. So I know that Ramsey type theorem or Wagner theorem are really famous, and it has been widely studied over the years by the graph theorists. And I think the problems of round robin problems or list orientation of graphs is also interesting. But can you give some idea to us whether these topics are difficult? I mean, how complex are these topics? Is it suitable if we give it to students for their thesis, their undergraduate thesis? Because for undergraduate thesis, I think they have very limited amount of time, like 4 to 6 months to study. Is it suitable for them? This question is for the three speakers.
So Professor Nakamoto should answer first. I'm already retired at university, so I have no responsibility for undergraduate students.
So yeah, I introduced very elementary graph theory topics. So I think some of our undergraduate students can study very elementary fact. Then I think some students can do something, I think. Yeah, that's all.
For me, it's a difficult question, actually. But as I told in my talk, if we consider some particular cases, only a fixed list or so small graphs, even for such graphs, there are some open problems, and I believe we should try those things first to solve for the general cases. So if I teach to my undergraduate students for that topic, I first ask them to read some proofs of our theorems, and then find some extension with maybe very restricted cases, but it's good to begin. And there are many important cases remains. Maybe that's only the small step, but that's necessary step, I believe.
Yes.
Yeah, it's all which I can say.
Okay, thank you so much. Yeah, I just want to give some idea for those who are new to this subject. So maybe we can start to explore this subject and start to do some small research on this subject. I think this kind of topics are really interesting for mathematicians especially. Okay, so is there any question from the participants? Enough? Okay. So I think that's all for the question and answer session. Let us thank again the three speakers for the informative and interesting talks. And thank you so much for the participants who are present on site and on the Zoom meeting. I hope that what we have learned today can give us broader knowledge and insight so that we can probably start research on this direction. Thank you, Professor Seiya Nagami, Professor Kenta Ozaki, and Professor Atsuhiro Nakamoto for the interesting presentation today. I hope that we can meet again in another occasion. Thank you.
Thank you. Thank you.
So we'll end this workshop here.
Okay. nice MC.
Okay, see you. Bye-bye, everyone. Bye-bye to all the participants.